asked by Chris to look into doing it. I've been to a few MLUGs and probably voiced my opinions on too many occasions, I guess. But yeah, so really, where I want to look at some of the fun I've had with the Scilab Gateway, and just before I go into things, just wanted to let everyone know that if you want to ask any questions at any point, just jump in. I think that's going to be the best way to do it. It seems to have worked so far. But I just want to ask, and I don't know how this is going to work, is anyone else familiar with Scilab, first of all?
Yeah, I've used it once or twice before. Kabul here, by the way.
Hi, Kabul. So just Kabul. So I'll get into what it is later. But I'm glad that's kind of there's only one person. That means there's going to be less people criticising my text-based language stuff. So. But yeah, essentially, it's an open source numerical tool, a bit like MATLAB, if anyone's used that. Basically, we use it for data analysis and control in our materials testing applications. So I'll just click on. So I wanted to give you a little bit of a background first. What we do, our hardware and software. And then move on to the Scilab stuff. I think it's relevant to kind of give you a little bit of a background on what we do, because everything I do after that kind of fits in. So I'm going to try not to bore you too much with that. I hope I don't. But it's I think it's relevant, so please bear with me, and we'll get on some demos later on. But yeah, so it's a bit of Scilab, and then introducing the LabVIEW Scilab Gateway, where it's, if anyone's familiar with the MATLAB side of things, it's very similar. Works like a script node essentially, but you put in Scilab commands into that.
Craig, there's a question come up from Steve about how does Scilab compare to MATLAB?
That's a good question. I think it's very similar. Obviously, it's open source, so there's not as much money plowed into it. It's therefore it's not quite as refined as MATLAB, although in some aspects it performs more quickly, because there's less in terms of error handling and things like that, and error checking. So there's a lot of plus and minuses. It's open source. It's free to use. It's free to use in an application that you sell. So it's in that respect, it's very useful, and from our point of view, and I'll get into it later, that's very beneficial. But many of the functions that you can do in MATLAB have a Scilab equivalent. A lot of them are very similar, in fact the same in some cases. But yeah, there's many equivalents. So that's it. Hope that answers your question. I'm not seeing the chat at the moment, so it's quite difficult to do that, to see that.
Craig, if you hover over the bottom of the view, something pops up and you've got some options, and one of them should be chat. If you hit that, it should come up onto the right hand side.
Ah, yeah, there we go.
Got it.
So, perfect. Thank you, Chris. I appreciate that. So MathCAD. Did you mean MATLAB or MathCAD? Steve.
Sorry, yeah, I may have I misread that. Yeah, sorry.
Okay, I don't know MathCAD. Sorry, so ignore my last answer.
That's my fault. Sorry about that. Some extra information there, though.
I'll have a look at that and get back to you later if I can. Yeah, basically move on to the LabVIEW Scilab Gateway, and then look at how we use that to kind of script in, so to make our applications dynamic in the way that they can do data analysis and some of the calculations and things like that that we do. And I'll put an example at the end, but I've got a few throughout. So I'll start with a bit of a background about us. Basically, we are Cooper Research Technology. We design and manufacture equipment, so based in the UK, design and manufacturing for preparation of and testing of road materials, so specialising in asphalt, but all these other materials as well, things that are used to make roads basically, and civil engineering stuff. Something that I never knew about at all before I joined the company. I had no idea what it was, and I didn't realise how much this was done around the world. We export something like 90% of our stuff. And it goes all over the world, and there's lots of people doing it. Civil engineering contractors, local authorities, national labs, universities, and other research places. Really, all looking at all looking at asphalt, which it just astounds me on a daily basis. So just wanted to go a bit into asphalt, really, just so you've got an idea of the background. I know this isn't related to LabVIEW much yet, but essentially asphalt's three components. You've got your aggregate, which is the stones and things like that, so all these big lumps of stuff. Then you've got your bitumen, which is the black sticky stuff which binds it all together. And then you've also got, in some cases, voids, which isn't this thing that we have in LabVIEW, an array of voids, but something, if you look in the picture on the right, this is just the gaps, so the air, and it's important in some cases for drainage, really, so you let in water through it, and that's it. One of the main aspects of asphalt in terms of the testing side of it is it's viscoelastic, which means that it doesn't respond to being squashed immediately. It has a bit of lag in there, which makes things very, very complicated. It behaves a little bit like a liquid and a little bit like a solid. So it makes things very interesting to kind of to analyze when you're looking at it. So some of our equipment is it's all about asphalt testing, really, but preparation. So we might be taking, on the left here, we've got a drill which drills cores out of the road, and then they're prepared in the lab, for testing in the lab. We have slab compactors, which makes like a big square slab of asphalt in the middle, and then a gyratory compactor on the right, which is making like a cylinder of asphalt, similar to a core, but one that you can produce in the lab. So these are the things for producing samples. And then we have some testing machines. So a lot of asphalt testing is quite empirical. People look at how it's used, and it's trying to replicate that in a lab directly. So running, as you can see on the left-hand side picture there, running like a wheel over it a number of times and seeing how it deforms and how resistant it is to deformation. The one on the right, you put loads of ball bearings in a pot and shake them up and down on top of the asphalt and see how it wears with abrasive materials on it. This is for things like where they use studded tyres in cold countries, seeing what the effects are on the asphalt there. So some real empirical tests, kind of real practical stuff. And then we have some more fundamental type tests where you're trying to find out the material properties, things like strength and stiffness and aspects like that, how it cracks and how it fatigues. So these are more fundamental tests, and the kind of tests that you might find in a generic sort of material testing laboratory, where you're testing metals or plastics and things like that. Asphalt has some, because it's viscoelastic, makes it difficult in that perspective, but it's similar to that. So that's kind of a quick, brief, hopefully, overview of what asphalt testing is and why we do it. And then, so really, it's not very related to LabVIEW at the moment, but essentially wanted to speak about why we use LabVIEW. As you can see, all our machines are sort of electromechanical things or pneumatics or hydraulics, but what we use to control the vast majority of them is a PC and LabVIEW, and it's we've got many different machines and many different applications, and they all using LabVIEW in some way or other. One of our Sorry, I'll just jump back onto that one. So one of our main bits of software for controlling, and this is a bit pertinent, the middle type of machine here, which is like a universal testing machine, which can do, perform lots of different types of tests on different shaped specimens and things like that. We have a piece of software called the universal software, which is heavily LabVIEW based. And that's what you can see on the screen here. So, kind of jumping on a bit, we have. I wanted to talk about our kind of hardware really a little bit, and our software, and our history in that a little bit, so that we could understand what I'm trying to talk about here. And so when we first, well, up until very recently, we had a very a bit of software called universal software, which was intended to be used on that middle type of machine, so the universal machine, which could do compressive, tensile, mixed mode testing of materials, static and dynamic applications. So you might be doing just holding a force or ramping a position, so you slowly squashing material, and it could be lots of different standards, so international standards, BS standards, EN standards, ASTMs, things like that, all the way to sort of highly flexible research level test methods, so where people wanted to do all sorts of new things that we haven't thought about to materials. So we had lots of different test specimen shapes and sizes, jigs and instrumentation, lots of load cells, LVDTs, things like that, for measuring the specimens, and then lots of different types of machines. So as well as that, the middle machine you saw on the slide before, we also have larger versions of it, with hydraulics, pneumatics, and also electromechanical actuators, so various different machines to control, and also ones which are a bit more complicated, which have sort of multiple axes and things like that, all of which you wanted to control from one platform really. And I think I've jumped on a slide there. So before we developed what I'm going to move on to next, we were a little bit stuck with that, because we had a very fixed system, a very sort of rigid system. It was a PCI card based 16-bit analog input, fixed transducer types, so they were all hardwired, so you couldn't change which type of feedback you had or anything like that. We had hardwired fixed feedback channels for the load, so you could only control in load control. We had potentiometer-based servo settings, so everything was done with little dial pots on the front of the panel and everything like that. So no real configurability. We had no emergency stop, and the software as well was quite rigid in the way it works. Calibration info is sort of manually selected. So if you changed out one of your transducers, you had to then manually set all the calibration settings and the ranges and things like that in the software. You had hard-coded data analysis, so when you got to research level, people wanting to do new things couldn't do new things, and similar with calculations to work out things like the stiffness or the fatigue life, things like that, and also control algorithms we couldn't play with and improve upon, without really developing the software further. releasing new versions. So that's a little bit of a background of where we were. So what we went away and produced was two things. One was this, which is our data acquisition and control unit, CDAC. That's with a C, not with a Q, for those NI people. It's 100 megabit Ethernet, so it really has the power to, or the grunt to give us the data that we need. It's got a SIL4 e-stop, so that's adequate for any application really that we work with. Serial comms for connection to things like environmental chambers, where we can sequence the temperature as well as and the environmental conditions, as well as the just the control on the actuator. So gives a bit more flexibility there. And then data acquisition, we can have up to 32 transducer input channels, 24-bit, 5 kilohertz, all with TEDs. So when you plug this transducer in, you actually straight away have all the calibration and the setup of the amplifiers and everything included in the plug of the device. So there's no manual, no user error involved in that part of things. We can have up to 8 servo outputs as well, so we can control up to 8 actuators all synchronously. With and that's with any of the channels that we use for data acquisition can be used to feedback, and we can have a combination of up to 4 of those to feed back to any channel. It's also got some digital I/O on there. It's fairly basic digital I/O, which is all we needed, but allows us to switch valves on and off and receive inputs from people, from users or from certain aspects of the machine. They're all opto isolated. And then sort of accompanying that, we have our dimension software, and this is kind of where we are going to look for the rest of the kind of the presentation is how this is used to set up a test, and also to analyze and calculate and control our machine, or the transducer in the machine. So dimensions used for configuration and use of CDAC, test sequencing, preloading standardized tests, but also allowing a fully customizable test sequence, and it does a lot of the kind of data analysis and stuff with Scilab. So that moves me on to the Scilab side of things. So as I've mentioned before, it's a open source software for numerical computation. So yeah, similar to MATLAB and possibly MathCAD, we'll see. It's and it's got since LabVIEW 8, there's had a simple sort of integration with LabVIEW via the Scilab Gateway, the LabVIEW Scilab Gateway. And I'll have a look. We'll have a look at that in a second. But the reason we needed Scilab really, or needed to introduce a method like this, I guess you could do this with LabVIEW in a way, but we needed a method to allow people to be able to do data analysis, calculations, control, but allow our customers and our internal staff to modify that data analysis without rewriting or re-releasing the software. So it allows us to really add new standards and new tests to the software without having to sort of reissue a newly developed bit of software. It's Scilab's open source, and it's quite a familiar sort of syntax for those using other numerical computation languages like MATLAB. Like I said, it's got a very similar interface and similar kind of commands, so it's nice from that point of view. because it's open source and free to use license, it's no additional cost of development. But more importantly, for our users, it means that they're able to produce new scripts and new analyses without any additional cost. It natively handles multi-dimensional arrays, and I think once you see that, it's quite a powerful thing. So you can do multiple sort of sums and things, or multiplications just in a one-liner. It's real nice. And then there's built-in functions for data analysis and control systems as well, which fits the job exactly. So just wanted to make sure I've not lost anyone, or anyone's got any questions at that point before we jump in.
I was just wondering, did you choose Scilab, or was that something that the users went?
Sorry, I can't quite hear you very well, Leah, sorry.
I was just trying to ask, did you choose Scilab, or was it something your users had used before?
It was something we chose, to be honest. So yeah, it was more based on what tools are available than doing any kind of user scoping out or anything like that. But it fits with. I mean, lots of people in universities use MATLAB, and therefore it made sense because the syntax was very similar.
Greg?
Hi there.
Sorry, just to go back to the actual transducer itself, is that, I guess, an embedded device that runs completely independently of, I guess, everything else then? So you poke it with your application, and it interacts with the rig.
The CDAC.
Yeah.
Yes, it is. Yes, it runs totally independently. Yeah.
Okay.
You can, whilst it's running, you can modify what it's doing, and that's where the iterative control side of stuff comes from.
Okay.
We can increase the amplitude and things like that. But essentially, yes, it's you tell it what to do and it goes. Yeah.
Right. Thanks.
Right, there's a question from Louis which says, "What is the advantage of using Scilab in comparison with using Python?"
Yeah, I thought that might come up, and that's why MathCAD threw me. But yeah, Scilab, I find it a much simpler development environment, and it's very similar to MATLAB. Yeah, you could use SciPy or various other tools in Python to do it. And to be honest, when we first started developing this, that kind of thing wasn't as prevalent as it is now. So yeah, I can totally understand why you'd use Python. I did very recently try to get into it a little bit, the Python side of things. I did find it much more difficult to get into than Scilab, and maybe that's one of the bigger reasons why we went that way. I guess you can see for yourself. Yeah, and Python is supported in LabVIEW as well. I was just seeing that question. It's true. I did wonder about doing allowing people to write in both, because that allows anyone to use it who's familiar with either language. So that was one option for me, but it's going to take a little bit of development to get that.
I guess when you first started this as well, Craig, like Greg said, that the integration with LabVIEW Python probably wasn't there. Is that
true? Yeah. I don't know when it was introduced to Python node. It certainly stuck out that Scilab was there when I started it.
I'm not sure about how the you would do the development in Python as well, because it looks like the Scilab comes with like quite a lightweight development environment, which is quite useful. Whereas I think unless you're using something else, you would be going through the console, your command line for Python, perhaps.
There is a Scilab, a Python node in more recent. I think that's what Greg was just pointing out.
Okay.
It's recently supported in LabVIEW. I still found it very tricky to kind of get things working in the right places. I never really got to the bottom of it.
Where you're given in the console screenshot you have there, where you can interact with the variables that you create. I don't know whether anything comes with Python natively that allows you to do things like that, whether you'd have to create something yourself.
Yeah, there are certain things for doing it. Those people who are more familiar with the Python side of things would probably be able to say, here's the way to do it. Jupyter springs to mind, and Anaconda, I think, are things for doing that. I'm saying that tentatively.
Python comes with idle IDE. It's very, very standard. It was very basic. It's similar to Notepad++, really.
Okay.
But Visual Studio Code is a really good free tool that I've used quite a lot for Python. The problem with LabVIEW in Python is, although it works, it can be tricky to get going. As Louis mentioned, it only supports Python 3.6 and 32-bit Python.
Yeah.
And you can also only call individual methods. You can't create a class or create an object of a class and, like you would standard Python programming, it's basically just, here's a method, here's your input, give me the output. And for those sorts of things, it works really well. But I've found it's quite limited in what it can do.
Okay.
That helps.
Well, hopefully, contrary to that, the Scilab side of things is, I think, is quite nice and straightforward. So I'll just have a quick run round the development environment, which I've put some slides up there, but I'm going to see if I can get my screen showing the development environment for you. If I can move that. So can everybody, I can't remember if I've shared my screen or just shared the presentation. Could someone just shout up if it's if they can see that or not?
I can see Scilab.
Thank you.
Yep.
Okay. So yeah, it comes with I think it's quite a nice little development environment, really. So you've got the main console where you can literally start typing in variables and things like that. So we can do a nice little 2D array there, and that's, so A is now a little 2D array. So I can now do A times 2, and it gives me the answer there. So real simple stuff. But everything, all the variables are all, like I mentioned earlier, they're all in multi-dimensional arrays. So you can have a 3D array, a 4D array, and it's just called A. So I can reassign it very simply. If I just want A to be a scalar, I'll just put A equals 1. So you don't have to redefine variables. You can even convert it to a string. Something like that, and it just goes straight into a string. There's no messing around with that. So I think from someone who wants to write a nice, who's not a programmer, but is an engineer or something like that, it's or a scientist, I guess, is really useful in that you're not having to worry about the kind of the low level syntax stuff. It's quite a high level language. So you've got a nice little place where you can mess around with stuff there. That's in the console, and then you've got your variable browser up here, which is also a pretty useful area as well. So if I just open up A, so if you just double click on A, it's going to appear on my other screen. So I'll drag that across. So you can see that A's just a 1D array, but now I can start messing around with that in here as well. So just close. Press enter. So now we've redefined that variable inside a little variable editor. So you can copy and paste directly from Excel in there and things like that. So I think the kind of environment's been really thought about, even though it is quite basic. You can also create some scripts. So if I just start this one, so if I put A equals 1, just do what we've done there. A equals everything's got to be semicolon ended, and then A times 2. Let's put B. So B equals A times 2. Now, if I just, I'm going to have to save that, but if I run that script, you can see that it's now created that new variable, and it's run that script, created that new variable B, and that is our A times 2. So that's kind of the real powerful bit about it. You can, I think it's very easy to start developing and playing around with things, and it has some real high level stuff in there for doing the data analysis stuff as well. It helps pretty good. You've got a nice browser for looking through all your functions there. I don't know, let me try something. So I'm going to multiply all the elements of, I've got capital lock on, multiply all the elements of A together. So that there. So I can now look at the help for that just by right click. Brings up all the description and everything. I find the descriptions really useful, and they're very well written. So just so you can see that. So yeah, for this one, it just returns the product of all the array elements. And then it does, I don't know if I should mention this one because I don't know too much about it. I did play around with it a long time ago. And anyone who's played with MATLAB will see some familiarity, but it's basically a block diagram based environment where you can, it's like Simulink if you've used MATLAB Simulink, where you can build systems out of blocks and run those, and it's very good for control systems, things like that. So I've put all the files when you're looking at saving files for or Scilab scripts, they're all in SCE and SCI files. Basically, one's for saving libraries of functions, and one's for creating a script.
Great, got a question from Leah.
Okay.
You seen that in the chat?
Yes, I can. So if you're using, it's a Simulink style thing, so you can use it in the loop if you wanted. It's very much been designed to be an alternative to Simulink.
Okay.
Okay, so I'm going to just jump on it. So all right, so I've done some examples already, but let's just do a few more in there. So I mean I don't know if I'm going to baffle people with some of some things, but I'll do some fairly basic matrix based stuff, and we'll see how we get on. So let's do A equals 1, B equals 2, and then C equals A plus 1. Simple stuff. Syntax is very easy, so I can do A divided by 1, A divided by B, multiply. So that's all with scalars. Now we can do exactly the same with complex numbers as well. So A equals 1 plus %i. Oops. So %i, that is just the imaginary unit. So now we have A is a complex number now. So I can do the square of A. We get 2i. What else? We could do some matrix as well. So let's say A equals 1, 2, 3, 4. Let's say B equals that. B that. I can now do A times B. We should get some complex matrix. So you can even do complex matrices, things like that. It's really powerful. So I just wanted to do some practical, quick practical examples of loading the scripts. Some of the things that I've played around with and done on that. Quite related to what we do on a day-to-day basis. So one of those, one of the things we do a lot is obviously waveform analysis. So we're looking at how to extract information from a transducer, and it depends on what kind of wave you're applying, but one of them that we use quite a lot is a Haversine. So I just wanted to show you what a Haversine was. Let me just try and pull this one up. Just a second. Okay. So I'll just run through a few scripts quickly, so we can see that. Yeah, that's a good one. So in this one, what I'm doing is trying to get a fit to a set of data, which is from a transducer, a position transducer probably, and one that has a pulse like this. It's trying to extract some information about that. So what you can see is the blue set of data is the raw information that we've fed in by the file that I chose, and then the green one is the fit to that data. it's not perfect in this case, because the actual pulse itself isn't the right shape. So you can see the red line shows you the error that we get from comparing that with a perfect pulse, and that's all generated in Scilab. So the data itself was from some tests that I ran on a dummy specimen.
So Craig, was that a script that you developed, or was that
yes,
Scilab based? That's yours, is it? Yeah.
Yeah, that's mine. Yeah. Most of that is dragging in the data, to be honest. So yeah.
So it's not like LabVIEW where you've got sort of built-in functions that you can sort of drag and utilize. Do you know what I mean? Or has it got that capability as well?
Well, yeah. It has got functions. Like I said, there's the if you look in the help, all these things are functions. So finding the absolute value of a number, making a complex number from the two parts, stuff like that. It's all there, so it's all blocked, but it's not as easy as LabVIEW in that you've not got like a nice palette to dig into. You've got to kind of, I guess in a way, you're looking through this menu here to see what you're looking for. There's lots of nice help and ways to get into it, but it's not quite as, I think on the interface side it's not quite as easy, but in terms of doing things with arrays and control and analysis stuff, it's very powerful.
Yeah, nice one.
One of the things I should say as well, when we get into the actual LabVIEW side of things, we sanitize a lot of this stuff, and the actual bit that we have our customers work on is just the bit that does the analysis, rather than having to drag files in or anything like that. So we use LabVIEW really to do all this stuff normally, and it does work. I mean, LabVIEW is much easier to work in that respect, I think. So that was really to demonstrate the kind of the bits that, I mean, that was producing a nice graph in Scilab. So it does have some user interface parts, but if you think LabVIEW is bad for user interface, then try this. Believe me, it's not easy. I'm going to skip over the last one. So we can move on to some LabVIEW side of things, which I think is where it gets a bit more interesting. So let's have a look at the LabVIEW Scilab Gateway. Basically, it behaves like a script node in LabVIEW. So I don't know if any of you have used script nodes before, but or MATLAB nodes, but essentially you can just type your MATLAB your Scilab into here to give you well, you can add inputs and add outputs to the script. I'll just dig into LabVIEW.
Craig, just a question from Steve on the chat there.
Yeah,
got it.
Yeah, well, it's the next thing on my list. So I was just going to open up a new VI so that we can have a look. So no, I don't want one of them. Let's have a look. There we go. Okay, so it's in mass. So you find it just there, hiding just below the MATLAB script. In fact, if you put MATLAB script on, I think you can change it. No, you can change it from the Scilab script to the MATLAB script. But essentially, yeah, you stick it on. It's already got error terminals on it. which I'll come to in a bit, then they're not the most helpful straight off. But then it's adding inputs, adding outputs, and then you can choose the data type there. So we've got real, complex, 1D arrays of real, 1D arrays of complex, 2D arrays of the same, strings, and then only 2D arrays of strings. I don't know why that's the case. You can put a path into it, which ends up being a string when you get it into Scilab anyway. Scilab handles strings and paths interchangeably. Boolean, and then 2D arrays of Booleans. So that, I guess that answers your question. You can't pass clusters in, and that's difficult. I guess a lot of it's the same with a lot of these interfaces with LabVIEW, is that clusters are pretty specific to LabVIEW, and I think anyone who's done any stuff with C# or .NET stuff might find the same. Shout up if you have. All right, maybe not then. But yeah, essentially you've got those data types. For me, that's perfect. That's what all I'm using Scilab for is data analysis, and the other things which are similar. What you do find is that without any sanitization, the error terminal is pretty rubbish. It's the same with the MATLAB node. I had a look at it recently. The MATLAB node gives exactly the same errors out. So you have to really do some digging. So if I just put, let me try this. So if I call my input variable A and I put A equals B, now Scilab doesn't know what B is. I'll put C, say, and Scilab doesn't know what C is. Tell you what, let's do A equals B, but we've put our output variable is C. So the Scilab script node doesn't know what C is. So I think in that case, it's going to cause no error. Okay, there we go. So here's the error that we get. Error occurred while executing script. Error message from server in Untitled 2. So you get literally nothing back apart from the fact that an error occurred. So without any sanitization of it, it's quite difficult to kind of understand. And what a lot of my time in developing this scripting tool, which I'll show you in a bit, is has been in sanitizing the errors, because you can get them out, but you have to do that in Scilab, and pass them to some outputs, and then convert them into errors to get your errors properly. So that's the Scilab Gateway. I think I put a link on earlier as to where to get that from. But if anyone wants it, then I can put that on to the chat at some point. So what we needed to do really to help with our application, or to make it work in LabVIEW well, was to start taking that a little bit further, and really using LabVIEW for the bits that we're familiar with, and then passing the kind of computational bits to Scilab, so kind of to doing the scripting really, and that's what I worked on next. So really passing scripts from LabVIEW to the gateway, executing scripts with something called xextra, which is one of the functions in Scilab, catching errors with the error catch function, and then really the rest of it is more how to deal with the data. So obviously what our tool should be able to do is pass in and out various size sort of data. So passing anything from a scalar to a multi-dimensional array, and also complex numbers if needed as well. Flattening, so really it's more about flattening that information in and out of the gateway. And then one of the things that we also needed to do is we'd like to be able to build up these scripts, and we want to run them all in Scilab, and then get all the outputs all at once. And the reason for that is that there's some overhead in actually just running the script itself, and if the more you can do inside it all at once, the less overhead there is in general. But also we can then pass information inside it to generate further results. We also wanted to make previous outputs available for next iteration, so that we can do things like iterative control or other various, cumulative results and things like that. So, I'll move on to the script here a bit. Is everyone all right with that?
I was going to say, probably got about 5-10 minutes, something like that. Does that work?
Yeah, I could probably rush through a bit of this. Do you want to? I mean, we could look at some examples rather than running through all the ins and outs. Would that be?
Yeah, whatever you think would. Yeah, if that sort of fills the time better, then yeah, that would be good. Yeah.
Okay. So I'll ignore the fact that there's all this stuff going in and out, and we'll have a look at some examples and see how that goes. And cool. If anyone's got any questions, then we can kind of run through it at the time. So quick example. Let's jump onto this bit. So what I produced really, I will dig into this a little bit, is a set of VIs to set up basically scripts so that we could pass a code, so some Scilab code, and do some work on some inputs and get an output. And all the kind of grunt work is done inside that run section. There. We've got a main code section which actually has the vast majority of the code. This bit is needed to run that and collect the errors from it, and the rest is more about so all the function either side are passing LabVIEW information into Scilab and then getting it back out again. So this one, quick multiplication. So here, just multiplying these two arrays together in Scilab. So the output one is the input one multiplied by input two. Simple. Let me just clear that array so you know it's actually been done. So there you go. So basically, just looking at the block diagram, we've got input one, added it into the script. Input two added into the script, added the code, and then we added that to the Scilab class, and then ran that inside run once. Then got the outputs. So getting everything. One of the things I should mention is that in Scilab everything's one indexed. So when you look at these indexes here, everything's one index rather than zero index, which is important. And that's why in the LabVIEW I've also made sure that that's one index, because it gets very confusing otherwise. Let's move on to some more examples. So doing some stuff with complex numbers there. So similar multiplication. So here I do a couple of things. So I do a multiplication first of the two arrays, and then a little bit of a modification to that is a bitwise operation. So that is doing rather than doing a matrix multiplication, it's just multiplying the corresponding elements. So the first element there, that multiplied by that one, the second multiplied by that one. So slightly different results from that. Also, what we can do is have two scripts running. So rather than just having one script running, we can use the results from the first script in the second script. So that's what I'm doing here. And basically this part of things here sets up the inputs to read from the first script, if that makes sense. So in this case, I'm doing the same as we did in the last one, but then I'm taking the output of, so this first output here, sorry, source output. So in fact, it's the second output. So I'm doing script 1, output 2, and I'm multiplying it by 1, and then inside here, I'm multiplying it by 2. So really, this result should be that output 2 multiplied by 2, which you can see is the case. And then the other thing we needed to do was a bit of iteration. So here's the another example where we're passing the results from one. So rather than just running this once, what I'm going to do is run it. Grab the wrong thing. I'm going to run it many times. So I've put my run once inside a loop, and we're going to update the graph at each point. So all I'm doing is multiplying the two arrays together, and then what we're doing is I'm splitting out the answer. It's a complex answer, so I'm splitting out the imaginary and real parts, and we're graphing them on the x and y axes, so you can see that there's the real part and there's the imaginary part. When we do that, so you can see that the results, this is a static script and static inputs, but multiplying that array by this multiple times generates this result. So each iteration moves it around a little bit. And then some stuff with error handling. So like I said earlier, there's a lot of issue with error handling. Well, not issue, but you have to do a lot of sanitization of the errors. So one of the things I did a lot of work on is getting that information out. So here's a script where all these forward slashes are comments, by the way. I've commented out these bottom ones because they're going to cause me errors. So let's just run that without. So initially we run it, and all we're doing is multiplying these inputs. Sorry, these numbers by together. What I do then is I do I've done a transpose on that matrix there. So because they're not the same size, or the number of columns don't and rows don't work in that case, we should get an error. So here you can see is the error information that got out from that. So that's all been sanitized by me after the script node, and then passed into the error cluster. So a number of different things.
So you had to run that in Scilab, have you then, Craig, to get that error information and transfer?
Yeah. So yeah, that's right. So if you look at this part of things, Chris, here is one part where I build up the error function, and I pass it out as a string here and an error number, and then do some extra work on that in LabVIEW to get that into the error cluster. So it's using that exec string there, and then catching the last error here and passing that into these values here. Yeah. Also, some of those values come out as 2D arrays, which causes you further issues. But so yeah, essentially what I've done is sanitize the output and give you some nice LabVIEW error information, so we can tell exactly which script it occurred in, what the description of the error is, the error number. So that's the Scilab error number. So in Scilab there's a big list of errors, and you can easily find what the error was. You can also find out which line it occurred on, and then if you did that, if the error occurred inside a function like it does in this particular one here, it also tells you which function that occurred in. So there you go. I'm going to see if I can. So how long have I got left, Chris? -1 minute?
Yeah, probably almost done now. Yeah.
All right. So I don't have to rush through to the last example, or just say thanks.
Yeah, if there's one quick example to do.
Yeah. All right. So one of the things that we do is something called a complex modulus, which probably doesn't mean anything to anyone here, but I'm just going to jump onto that one. It sort of puts it all together, if that makes sense. Just grab that out. So apologies for the messiness of this VI. It's quite large, but this was done when I was trying to throw it together as quickly as possible. But essentially, what I've done is set up a lot of different scripts. So each of these pages has a different script. I'm sorry for using tabs. But so we do some analysis on the data, we pass it to a calculation, and then we control the system. So I've got a little bit of a simulated system in here. So what have we done there? This might be a live demonstration that doesn't work. Yeah, it looks like it's not going to work, that one. So I might pass on that. I did test it out yesterday.
Always the way. It's always
Yeah.
It's good to see some realistic code going on at these user groups.
Yeah. So yeah, I think I've probably overstepped the mark with that one.
No, that's good. That's really great. Great presentation and interesting insight into something that I definitely haven't had experience with, and it's good to see it being used somewhere and be exposed to it, I guess.